Hello everyone. Today I'm going to talk about robotic information gathering via deep generative in painting, and this work is supported by NSF CPS grants, and we are the authors from University of North Florida and University of Central Florida. So in this paper, we study the problem of information sampling from an unknown environment using a mobile robot. So if the environment is very large, collecting information from all the environment becomes prohibitive because the robots might not have enough battery to cover the whole environment. Therefore, the objective for the robot will be to collect information from k locations in the environment and infer the information in the remaining locations. So the main challenges that we try to focus on in this paper are most of the studies in the literature assume that the information field is Gaussian and therefore Gaussian process regression can be used. However, that might not be the case in the real world. GPR, on the other hand, has high time complexity and cannot be scaled to thousands of information points in the environment and in its standard form. So here is the main architecture or framework for any informative path planning model. So what happens is the robot starts the path planning from the current location. It infers the sensor measurement in the rest of the locations in the environment, and from there it decides which points to go to. So that is the module of path planning, and it keeps happening back and forth. So in this paper, we try to focus only on the inference part of the informative path planning framework and not the path planning portion itself. So the main contributions of our work are as follows. So we propose a novel technique of inference in the robotic information gathering problem based on the techniques inspired by image in painting literature. We show that the proposed inference model provides comparative solution quality but scales significantly better than a GP regression technique or the standard approach to the robotic information gathering. Now on the right hand side, you can see three examples of different types of inferencing tasks that we have implemented in this particular paper. So on the left hand picture, we see that the yellow area indicates that where the robot could not take data from. On top row on the right hand side, we see this is a speckled mask. So that shows that there are multiple points randomly distributed across the environment where the robot could not get the information from. And on the bottom, we see that the black area is where the robot could get information from, but whereas the white cells where the robot could not get any information from because the robot sensor might not be working, or robot probably did not have enough battery to cover the whole environment. But regardless, our goal would be to infer information or sensor measurements in all these unseen locations using the deep in-painting technique. So we would like to point out that there is a subfield in machine learning that is dedicated to finding efficient solutions using sparse GPs that can scale up to thousands of information points, but that is usually not employed in the robotic literature. So on the right hand side, we show that the most prominent state of the art and where information collection has been modeled using Gaussian process regression, and what is the environment size in those studies. So that what we can see here is the maximum number of cells or nodes that have been used is 9,000 or close to 9,000, whereas our paper we go up to 1 million data point, so which is much higher than the state of the art that we can find in the literature. We argue that instead of using GPs, a different approach can be taken to solve the information gathering problem without relying on this carefully designed and sophisticated sparse GPs like Solin et al. Has done in their work. So the particular technique that we use in this work is called inpainting. So early approaches to image inpainting aim to expand the current texture of the image in a local neighborhood, but this might not be good for large infilling tasks where you have to remove that yellow box that I have shown in a few slides back. While we are interested in a semantically correct infill, but the visual realism is not the main requirement, because that might be useful in machine vision tasks, but for us, as the robots are collecting information, therefore global reasoning is also more important. For example, if you see that one part of the agricultural field is diseased, how do you reason in the other areas whether that part will be diseased or not? So that is important for us. Now, in this paper, we use a technique called DFIL version 2, which is due to Yu et al. Is a promising approach that uses a model called gated convolution, which learns the contributions of the various types of nearby pixels alongside the different features for each spatial location. It uses a variant of GAN, so that is generative adversarial network, called spectral normalized Markovian discriminator, which generalizes the concept of local and global GANs. Now we compare our approach with a Gaussian process-based technique, which is our main baseline. So GP models assume that all the locations generate information according to a Gaussian random vector X, and the mean vector is known, the prior mean vector before any information has been collected, that is represented by mu, and the covariance matrix is there, which is the sigma. We assume that the robot usually has like negligible sensor noise for this particular work. We have assumed an exponential kernel available in the GP for this paper. That means that the correlation between 2 points reduces exponentially on their geographical distance. So the more the distance, the lesser the correlation will be between 2 locations in the environment. Now, for the simulation work, we have 2 types of data that we have used to verify or validate our technique. So first is the synthetic data that we have created by ourselves on our computers. So that contains 3000 images of size 32 by 32 pixels, and these are 8-bit grayscale images. Now, Gauss fill is the process that we use to find the optimal solution. It has the knowledge of prior statistics that produces the synthetic data, and that can also output the optimal prediction in the minimum mean square error sense. So it will basically predict something that will have the least difference or least error with the ground truth. Now, the second type of data that we have used in this paper is a real world crop data. One set of 32 by 32 images are there, and a different set contains 1024 times 1024 images. These are all 24-bit color images in JPEG format, so we had to convert them to grayscale images that I'll talk about in the next slide. Now, all the high resolution images first were downsized to match the 1024 by 1024 uniformly across all the images. Now, this is an example that we have used. So initially, we start off with this high resolution image that is part of this cropland dataset. And as you can see in this example on the right hand side, this image has a size of 3456 times 4608 at 6 feet resolution. So this is a 24-bit color image. Now, first what we do is we make it 8-bit grayscale image and also downsize it to make it a 15-bit version. So 15-bit version resolution. So that's what we have done on the picture B that you can see there. Next, a pair of square images that you see in the bottom, so in here and in here, they are at either 1024 by 1024 resolution or 32 by 32 resolution that has been used for further testing. Now, this is the first set of results that we present. So this result is presented for robot path mask. So that means in this mask, the robot has covered some part of the environment and the remaining part has not been covered. So actual random path has been used for this. So as you can see, with deep field, the mean square error with the ground truth is 16, around 16. With Gauss field, it is 7. Whereas average field, that is another baseline we use, that has a mean square error of 197. So although it performs worse than Gauss field, which was assumed or to be understood, but at the same time, you have to take into account that it is not as bad as the average field. On the other hand, we compare the block mask and speckle mask images. with deep field, Gauss field fitted, and average field with optimal. So as can be understood, the Gauss field optimal perform the best because this gives you the optimal result in terms of mean square error. So that is 6.85, and Gauss field fitted is also close to that. That is 9.33. And in our case that is 15.78, whereas in average field that is 200. One thing to note here, as block mask, it is the one block of the whole picture is missing. Remember that yellow block that I have shown in the earlier slides. So matching or finding or filling those pixels is a difficult task because so many pixels have to be filled at the same time. On the other hand, with speckle mask, every algorithm perform better. So as you can see, even the Gauss field optimal is lower than this block mask, so it is 2. However, interestingly, our approach performed almost 3 times better than the block mask cases. Now next we show when our algorithm is using the actual cropland images, real world cropland images, and in that case you can see with block mask and our algorithm is very close to the Gauss fill MSC in this particular scenario. And the reason for that is in the previously the synthetic data was generated from a Gaussian distribution, so Gauss fill was a better fit for that. But as we have argued in the beginning, that Gaussian process might not be the best case scenario for non-Gaussian data like the real world cropland data that we have here. So therefore our algorithms MSE and deep fields MSE and Gaussian fields MSE are very close to each other. Similar thing can be noticed for the speckle mask as well. And as I have mentioned before and described before, that now the MSE values has gone down for speckle mask images. For 1024 by 1024 images, Gaussian field could not be scaled to that value. So as we have discussed, that is another drawback of GPR technique. And in our case, we see that even when the size of the image has increased by this much, only the MSE has only doubled. So that is a good scaling of our technique that we can demonstrate here. So these are some illustrations. So this is a block mask that we have used, and this is speckle mask that we have used. These are all on 32 by 32 cropland images, and this is the corresponding deep field version on the left hand side. This is the Gauss field version, and this is the average field version, and the corresponding MSEs are also mentioned here. And this is another illustration, but this is for the robot path mask. As you can see, this is the ground truth image, and this is the path mask that we have used. Again, black cells are where the robot has been, and the white cells are where the robot has not been. Number C shows the deep field version of it, which has the MSE of 17. Number D shows the Gauss field, which has the MSE of 3, and finally the average field has the MSE of 329, which can be easily viewed on the on this side. So in conclusion, we can say that we leverage the recent advances in deep neural networks and image painting techniques for information modeling tasks. Unlike Gaussian-based models, the Inpainting techniques do not require the underlying information field of the ambient phenomena to be Gaussian. Used a state-of-the-art Inpainting technique for such an information modeling task on both synthetic and real-world crop datasets. Experimental results show that our proposed Inpainting based inference technique is extremely fast, and it performs comparably against the GPR technique. Also, it outscales the GPR regressor. In the future, we plan to integrate an online path planning framework with this model, so the whole informative path planning framework will be running based on this inference technique. Thank you for attending and listening to this talk.